Drop a needle on a wooden floor. Just a needle. No circles, no compasses, no geometry homework. And yet, if you count how often that needle lands across the cracks in the floorboards, hidden inside that number is pi. The same pi from circles. On a floor. With a needle. This is going to keep happening, by the way. Pi is going to show up in rivers, in the bell curve from your statistics class, and in a sum of fractions that has absolutely nothing to do with anything round. And every time, we're going to ask the same baffled question. What is the circle number doing here? The answer is the twist. Pi was never really about circles. We just met it there first, like meeting a celebrity at a coffee shop and assuming they live there. Let's start with that needle, because it's the most outrageous one. In 1733, a French naturalist named Georges Louis Leclerc, the Count of Buffon, a man with so many names he clearly had time on his hands, asked a simple question. Take a needle of length L. Take a floor with parallel lines spaced exactly L apart. Drop the needle. What's the probability it lands across one of the lines? The answer is 2 divided by pi. Roughly 64%. Go ahead, read that again. We started with a needle and some floorboards, and pi crashed the party uninvited. Now, mathematicians love this because it means you can compute pi by throwing needles at the floor. Drop 10,000 needles, count the crossings, do a little division, and out pops 3.14. It is the world's least efficient way to calculate pi, and people have absolutely done it for fun, which tells you everything you need to know about people who do math for fun. But why pi? Where's the circle? Here's the thing, when the needle falls, it doesn't just land in a position, it lands at an angle. It could point north, northeast, sideways, any direction at all. And how do we measure all possible directions? In a full turn. In angles that run from 0 all the way around to 2 pi. The rotation was hiding in the problem the whole time. The needle spins as it falls, and the moment you have rotation, pi is already in the room, quietly judging your floor. Hold on to that idea, rotation, because it's about to explain everything. Let's go outside. Way outside. Let's look at rivers. If you measure how long a river actually is, every twist, every bend, every lazy loop where it can't decide where it's going, and you divide that by the straight line distance from the source to the sea, you get a number. And across hundreds of rivers, all over the planet, that number averages out to about pi. I want to be clear about how strange this is. Nobody told the Amazon about pi. The Mississippi did not take a geometry course. These are giant ditches full of water, and they have collectively agreed to wander about 3.14 times farther than they need to. If a river were a person, it'd be the friend who turns a 10-minute walk into an hour because they know a shortcut. So why pi again? Because rivers meander. They don't bend randomly. They curve back and forth in a shape that's roughly a sine wave. And it turns out that if you measure the length of one full wave of a sine curve and compare it to its width, pi shows up. The river is oscillating. And there it is again, that word. Not rotation this time, but its close cousin. Repetition. Periodicity. The thing that comes back around. Now let's go somewhere with no needles and no water at all. Let's go to your statistics class, to the most famous curve in all of science. The bell curve. The normal distribution. The thing that describes heights, test scores, measurement errors, and how late your friends are to dinner. The formula for the bell curve has a pi sitting right in it. Specifically, you divide by the square root of 2 pi. And every statistics student who's ever seen this has had the same thought. I'm sorry, what is the circle number doing in my probability formula? There are no circles. There's a hill-shaped curve and a lot of anxiety about exams. Where's the pi coming from? This is where it gets genuinely beautiful. The heart of the bell curve is a function shaped like e to the negative x squared, a nice smooth hump. And mathematicians wanted to know the total area under that hump, all the way out to infinity in both directions. This is called the Gaussian integral, and the answer is the square root of pi. The proof is one of the great magic tricks in mathematics. You can't solve this integral directly, it stubbornly refuses. So instead, you take the integral and you square it. Now you've got two of them, one running along x and one running along y. And suddenly you're not on a line anymore. You're on a flat plane. And the function on that plane is shaped like e to the negative x squared minus y squared. Here's the punchline. That expression, x squared plus y squared, that's the distance from the center. That's a circle. So instead of using square coordinates, you switch to polar coordinates, where everything is measured in radius and angle. And the moment you do, the problem cracks open like an egg, and pi falls out. The circle was hiding in the geometry the entire time. We just had to leave the one-dimensional line and look from above to see it. So pi isn't a guest in the bell curve. Pi was an architect. We just couldn't see the blueprints from the ground floor. Now let's talk about the equation that mathematicians put on tote bags. The one they call the most beautiful in all of mathematics. E to the power of I times pi, plus 1, equals 0. This thing connects 5 numbers, e, I, 1, 0, and our friend pi, and it does it so cleanly that grown mathematicians have been known to get a little emotional. But let's strip away the romance. Why is pi in here? Because e to the power of I times something is secretly a circle. When you allow imaginary numbers into the exponential function, it stops growing and starts spinning. As that exponent increases, you don't shoot off to infinity. You trace around a circle, forever, like a horse on a carousel that's mildly concerned it'll never get off. And how far around that circle do you go when the exponent hits pi? Exactly halfway. Half a turn. And where do you land after half a turn? On the opposite side, at -1. So e to the I pi equals -1, and adding 1 gets you to 0. The whole equation is just a fancy way of saying, go halfway around the circle, and you end up across the street. Pi isn't decorating this equation. Pi is the half circle. The exponential function and the circle turned out to be the same creature wearing 2 different costumes. Are you starting to see a pattern? Because I've saved my favorite for last. In 1734, a young Leonhard Euler, the most prolific mathematician who ever lived, a man who kept publishing papers for decades after he went blind, which makes my excuses about being busy look pretty weak, tackled a problem that had stumped everyone. Add up 1 plus 1/4 plus 1/9 plus 1/16, the reciprocals of all the perfect squares, forever. What do you get? The answer is pi squared, divided by 6. I need you to appreciate how unhinged this is. We are adding up plain fractions. 1/1, 1/4, 1/9. There is nothing round here. There is no spinning, no needle, no river. It is the most boring-looking sum imaginable. And out the other end comes pi squared. It's like baking a cake from flour and eggs and pulling a live circle out of the oven. How did Euler do it? He connected the sum to the sine function, the wave that endlessly rises and falls. Sine crosses 0 at every multiple of pi. At pi, at 2 pi, at 3 pi, on and on, spaced perfectly. Euler wrote sine as an infinite product built out of those evenly spaced crossings, and when he matched the pieces up, the sum of the squares fell right into place. And the engine underneath it all? Sine. A periodic function. Something that repeats. There's that word again, for the 5th time. So let me say the thing this whole video has been building toward. Pi is not the circle constant. Pi is the rotation constant. It is what shows up whenever something turns, oscillates, cycles, or repeats. And once you know that, you start seeing it everywhere. The pendulum on a grandfather clock? Its period is 2 pi times the square root of length over gravity, because it swings along an arc, and its motion is a perfect sine wave. Pi shows up in Fourier transforms, the math that breaks any sound or signal into pure spinning waves, which is how your phone compresses music. It shows up in Heisenberg's uncertainty principle, deep in quantum mechanics, where particles behave like waves. It shows up in the distribution of prime numbers, through the Riemann zeta function, and the primes, somehow, are secretly oscillating too. The deepest reason ties it all together. Pi is the half period of the exponential function when you feed it imaginary numbers. It's the spin built into the very machinery of math. And complex exponentials, those little spinning carousels, are hiding underneath waves, probability, physics, and prime numbers alike. So wherever they go, pi follows. That needle on the floor was never really about a needle. It was about angles. The river was about waves. The bell curve was about a hidden circle in 2 dimensions. And the most beautiful equation in math was just to walk halfway around a loop. Pi isn't a circle number that got lucky and went viral. It's a rotation number that happens to be easiest to spot in circles. But it's been in your bell curve, your river, your pendulum, and your prime numbers all along. Because every single one of them is, secretly, spinning. If this rewired how you see that little 3.14, do me a favor, like the video, share it with someone who thinks pi only lives in geometry class, and subscribe to Improper Integral for more visual math and science. We'll keep chasing the patterns hiding in plain sight.